Hey guys, as you can tell, I am not here this morning for you, unfortunately, so I apologize for that. But if you are with me, we are going to be doing the eye today. So what I've done is I've created a little screencast video to help you through today's lesson. So today we'll be going over the eye, dysfunctions of the eye, and then we'll flip-flop with Fez's group tomorrow, and you'll be with Fez going over the ear, components of the ear, and dysfunction in the ear. So let's just take a look at what we've covered so far with the eye. So you all should have a diagram like this labeled. So you should have something like this in the booklet that we've done. So did the color-coded drawing. Okay, this is a cross-section of a human eye, and you should be familiar with most of these components. These are the major components or structures within the eye, and you should be able to identify their location as well as the function of the component or the structure in the eye. So what it does in the eye. If you don't know all the components yet, I would definitely recommend looking over them and being ultra familiar with them. You are going to need to know them for both the exam as well as the diploma, so just make sure you know again that function and structure location within the eye. Okay. So here's an interesting little video that I'm going to play for you about perception of the eye, or what we perceive in our environment. So it's really interesting because your brain has a great deal of impact on what you perceive versus what your eyes bring in as sensory information. So sensation is different than perception. So essentially the video explains about how your brain has an impact on the image that you are seeing. So let's take a little look at the video, and then I'll briefly discuss it at the end of the video. So we'll watch the video together and then have a little discussion at the end here about what it really means. So let's take a look. Oops. See if I can get it to play here. There we go.
Do you know what you're seeing?
Okay, sorry about that. I just skipped the ad there for you, so
Our
let's try
perception
that
of the
again.
world around us is strongly linked to our vision, but how do you know what you're seeing is real? Can you really trust your eyes? Take for example these two gray rectangular columns, both of which are different shades of gray. Or are they? It turns out that they're the exact same, and yet even after knowing the illusion is there, your eyes refuse to see them as the same. Introducing colors produces the same result. I promise, no trick photography or editing effects have been applied. In fact, if you look up the Munker white illusion, you'll come across many more examples. Examine them in Photoshop and you can see that the colors are the exact same. A similar effect can be seen with this checkerboard illusion. Tile A clearly seems darker than tile B, but you know better by now, right? Even though your eyes can't see it, you know when I remove the surrounding imagery, the tiles will be the same color. So what's going on here? The truth is that scientists don't fully understand this phenomenon, and there are many complex biological and neurological factors taking place. Ultimately, our brains judge color and brightness in context. In other words, our brains compare the surrounding environment in order to create our perception. The purpose of our senses, or eyes in this case, is not to provide us with an absolute color or physical property of our external reality, but to interpret what we see as efficiently as possible in order to interact with our environment most appropriately. The tile illusion takes advantage of this phenomenon. Our brains know that shadows make objects look darker. As a result, the brain compensates by interpreting the tile as being lighter than it appears, until we take the shadow away. Perhaps the most blatant example is this gradient. The middle bar is simply one color. Remove the background gradient and it becomes obvious. Once again, the darkness of the background has affected our perception of the bar's color. Our perception is relative. So, do you still trust your eyes? Got a burning question you want answered? Ask it in the comments.
So I think that it is super interesting. That video is very interesting as to how your brain has such a big impact on creating the image that you see. So they used some examples of optical illusions in demonstrating the difference between sensation and perception, pardon me. So I have created a link on the website. So if you go to the teacher pages, if you go to the Ponoka Secondary Campus website, click on teacher pages, and then choose Miss Anderson's class site. Okay, or you can simply just go to teachmissanderson.weebly.com. You'll go to the Bio 30 tab. You'll see that I've added another page here called Lessons, and you can just go to the lesson called The Eye. When you scroll down, you may see some different links here. This is where you will see the video that you're watching right now linked. And I want you just to click on PSC Science Resources. This is an additional page that I have created with some science resources that you might find helpful in some of your science classes, especially biology. So when we go to Bio 30, I want you to click on the Nervous System and Endocrine System tab and just scroll towards the bottom. You'll see some of these additional videos that you're more than welcome to watch, but I would like you to just take a look at some of these optical illusions that I've posted at the bottom. So again, we look at some optical illusions and we see how sensation is different than perception. So if you view one of these discs, and if you look at it straight on, you might notice that the disc seems stationary, while the surrounding discs around it seem to be rotating in a different direction. Again, this is an optical illusion based on the image itself creating a different perception in our mind. Now, as you scroll through some of these, again, it is trickery based on the creation of the image and how the image was created. So this may look like you're sort of inside a tube and it's spinning. And this is simply just because of the shape of the orange dots that are present, as well as the fact that you'll notice that on one side of the dot there is a white line, and on the other side of the dot there is a black line, creating an illusion of this rotating. Now I'd like you to flick through some of these optical illusions. You might notice that some of them have some pretty interesting effects on what you perceive. So in this example, you're going to want to look at this black section here and see that what the surrounding image does. And as you shift your eyes across the image, you might notice that it almost appears that it's swirling. You can continue to look through some additional optical illusions that I've posted here. Some of them might be familiar to you. Some of them might be new, so maybe you can just take a look and see if you recognize any of these optical illusions or what the optical illusion is. If you want me to explain them, come into MEST and I can give a little bit more description on what the optical illusion is and give you more reason behind why I chose these ones. So let's go back to the slides here and talk a little bit more about color perception. So essentially, color perception is due to the presence of cones in your eye. So cones are responsible for color detection, and color detection is due to higher intensity of light. So in bright light, we generally see more colors. Now remember that we have the highest concentration of cones present in the fovea centralis in the eye. So that's that section right behind the pupil in the retina in the eye. Now cones are responsible for detecting color, and we have 3 different color detection cones. We have red, blue, and green color detection cones. So when combinations of cones are stimulated by different incoming light, the brain perceives different colors. So a variety of these different cones firing in different combinations and with a different intensity of light allows us to see millions of shades of colors. So instead of seeing something that is simply red, blue, or green, we might be able to see a variety of colors such as this. Notice that at the top we have less of a blue cones firing here. We see primarily red and green colors, while towards the bottom we see an increase of the blue cones firing, allowing us to see more blue color. Now you'll notice that the variety across this grid here shows that we can see millions of different shades, and we can differentiate between the shades of colors in general as well. Focusing on an image is also a specialized function in the eye, controlled by ciliary muscles that surround the lens. So ciliary muscles control the shape of the lens, either allowing it to be thicker or narrower, changing the amount or direction of light coming into the eye. Sorry, not the amount, I should say bending. It changes the bending of the light in the eye. So images that are close require a thicker lens, which is based on the ciliary muscles contracting, creating a thicker lens. This provides more bending of the light for near vision. Distant images require thinner lenses where muscles relax, changing the bending of the light to focus the image on the retina for distant images. Okay, so this changing of the lens due to the ciliary muscles, as well as adjustments made by the pupil, is called accommodation. It's basically how your eye adjusts to focus on an image, whether it be near or far. Okay, the accommodation reflex also involves your pupil dilating. So for distant images, your pupil will dilate, and for close-up objects or images, your pupil will constrict. As you can imagine, further objects that are further away require more light to come into the eye to focus on that image. Okay, let's talk a little bit about color blindness. Now this is getting more into the defects of the eye, and color blindness is for sure a more interesting defect of the eye. So this occurs when either there's the lack of presence of cones in the eye, or there's a certain cone that is defective in the eye. Okay, color blindness is more common in males, and its most common type is of the red-green color blindness. So that is where we see most people that express color blindness is in the red-green range. So this is a simple color blindness test. It's more extensive now, but this is sort of what we've used in the past to test for color blindness. So what you'll see is a variety of circles that have either a number or a symbol or an image inside, and it's represented by a bunch of small or different shape or different sizes, pardon me, of dots, creating an image. Most people should be able to see this dot with the number 12 inside it. Regardless of if you have color blindness or not, you should be able to see this. This type of color blindness would be a very rare form, but there is enough contrast between the two colors to create the image with the number 12 in it. As I continue, these are going to get a little bit harder or trickier to see. This image here, again, is a color blindness test. This is for red-green color blindness. Now, if you have normal vision, you should be able to see that there's the number 8 inside of this circle here. So we have the green dots around this, and we have the 8 on the inside. If you have red-green color blindness, you may find it hard to see the 8 or impossible to see the 8 inside this green circle. The next image is even harder. Okay, it is again testing for red-green color blindness. Some of you, even with normal vision, might take a minute to focus, but in this image here, you should be able to see the number 5 inside in green dots inside of this sort of orangey red circle. Again, testing for color blindness. If you cannot see that 5, you may have red-green color blindness. Now I can only record up to 15-minute clips of the video, so this is going to end the first part of this lesson on the eye. To see the next section, please go to my teacher page, teachmssanderson.weebly.com, to view the next part of this lesson.